All right, let's pull back the curtain on a piece of computer science that honestly feels a lot like real-life magic. We're talking about the hash table. It's the secret sauce that powers some of the fastest software you and I use every single day.
So let me just start by asking you this. Imagine you've got a database with millions, maybe even billions of user profiles. How in the world do you find just one of them without having to scan through every single entry? I mean, the brute force way would take forever, but there's a way to do it in the blink of an eye.
And yeah, you guessed it, the answer is the hash table. This is the absolute powerhouse behind things like Python's dictionaries or Java's hash maps, the reason they feel so instantaneous. For our purposes today, this is the hero of our story.
So what's the big promise here? What's the whole point? It's all about getting this near instantaneous access to our data, no matter how ridiculously huge our dataset gets. To really get this, let's use an analogy. Just picture a gigantic wall of mailboxes, each with its own unique number. Now, if you knew exactly which mailbox your letter was in, you could just walk right up to it and grab it. No searching needed. That right there, that's the goal.
So how does this actually work? How do we know precisely which mailbox to go to every single time? Well, that's where the process of hashing comes into play. The process is actually pretty straightforward. You start with a piece of data you want to find, which we call a key. In our analogy, that's just the name on the letter. You then give this key to a special hash function, which you can think of as a super efficient postal worker. This function instantly does a calculation and spits out the exact bucket index, or, the mailbox number where that data belongs.
But, it sounds a little too perfect, right? And, well, it kind of is. This system isn't flawless. There's a fundamental challenge that every hash table has to deal with, and it's called the collision problem.
So think about it. What happens when our postal worker, our hash function, takes two totally different names, but the calculation ends up pointing to the exact same mailbox number for both? Now you've got two items that need to go into a slot that was really only built for one. This is the central conflict in the world of hash tables.
And this brings us to the formal definition. A collision is just what happens when two unique keys get mapped to the very same destination. And it's not a mistake, it's actually an inevitable consequence of trying to squeeze a huge universe of possible keys into a much smaller finite number of buckets.
So the real game isn't trying to prevent collisions, because that's pretty much impossible. The trick is to handle them gracefully when they happen. And engineers have come up with two really clever strategies to do just that.
These two main approaches are called separate chaining and open addressing. With separate chaining, you basically just let each mailbox hold a little list of items. But with open addressing, if a mailbox is full, you just look for the next available one based on a specific pattern. And as you can see, each method has its own pros and cons.
Let's go back to our analogy for separate chaining. It's really simple. When two different letters get assigned to, say, mailbox number 42, you just put both of them inside. The mailbox now holds a small list. To find your letter, you go straight to the right box and just quickly glance through the handful of items in there. Easy.
Now, open addressing is different. The rule is strict. One item per mailbox, period. So if mailbox number 42 is already taken, our postal worker follows a predefined rule, something like, okay, check 43, then check 45, then 48, and so on, until an empty slot is found. This whole process of searching for an open spot is called probing.
Okay, so we've got our system, we know how to handle collisions, but how do we make sure it actually lives up to that promise of being almost instant? How do we keep it fast?
You've probably heard this phrase thrown around, maybe in a computer science class or online. People say that hash tables have O of 1 or constant time performance. In plain English, that's supposed to mean that the lookup time is always the same, whether you have 10 items or 10 million. Yeah. That's not the whole story. In fact, it's one of the biggest misconceptions about this data structure. That O1 promise, it comes with some really important strings attached.
The truth is, O of 1 is the average and the expected case. When everything's humming along nicely, your hash function is spreading things out evenly, and the table isn't too full, then yes, you get that magical, instantaneous speed.
But then, there's the worst case. This is what happens if you have a terrible hash function, or you just get incredibly unlucky, and every single key collides into the same bucket. Your beautiful, fast hash table suddenly becomes nothing more than a single, long, slow list. And finding an item means scanning through every single element. That's a performance of O of n, which means the search time grows with the number of items. It's a total breakdown, the very thing we were trying to avoid.
So this is the million-dollar question for any engineer using a hash table, right? How do you make sure you stay in that happy, fast, average-case world and avoid that catastrophic worst-case scenario?
And thankfully, the answer really just boils down to two critical things. First, you have to use a high-quality hash function, one that acts like a great postal worker and spreads the mail out evenly. And second, you have to control something called the load factor.
The load factor, which we often represent with the Greek letter alpha, is actually super simple. It's just the ratio of items in your table to the number of available buckets. If your load factor gets too high, let's say your mailboxes are 75% full, the chance of collisions just skyrockets. So to fix this, a good hash table will automatically resize itself, adding way more buckets to keep that load factor low and keep performance high.
So let's bring it all home. The magic of the hash table is its promise of super fast O of 1 lookups on average. It does this by using a hash function to instantly map a key to a location. But we've learned that collisions are going to happen, and managing them is crucial. And maybe most importantly, that legendary speed isn't a guarantee. It's something you have to maintain by using a good hash function and keeping a close eye on that load factor.
And that brings us to a final thought to chew on. Hash tables are absolutely amazing for direct lookups, but they don't care about order. You can't ask a hash table for all users whose names start with letters between A and C. So, the question I'll leave you with is this. If they're so fast, when do their limitations make other data structures, like maybe a tree, the better tool for the job?